Welcome everyone to part 3 of the Acreon tutorial series where I'm looking at the quarter car wheel model and performing H infinity control now in part 3, which will just be static weight, and where we're basically trying to reject a road disturbance and then model it for a robust ride with the performance criteria. And that'll be enumerated in this section, what that actually means. So in part 1 and 2, part 1 I looked at or did the derivation of the quarter car wheel as a spring mass damper system with the hydraulic cylinders and actuator, did it in the direct Newtonian approach to get the dynamics, and then the linearization was straightforward because it was already linear, but the big thing was the change of coordinates to the perturbance state. And so from there, we looked at the state space open loop and we saw that it was stable. We looked at the Gramians for controllability and observability, and I showed how that C, which was basically the suspension limitation from the body to the wheel, how that was taken, and then the other criteria was the body velocity term. That'll show up again on the observer part of this. Right now we're focused on the state feedback, and so we're going to have a performance ZP output, which is similar to the H2 synthesis that was done in the cart pole example. And so the criteria here is going to align nicely with the observer once I do that synthesis for the full output feedback with the dynamic compensator design, which would be, I think at part 4. So I'm jumping the gun again a little bit, but just interlude. Right now we're focused on just the state feedback with this ZP performance output space. So the continuous plant is the same form here. I do have the feed through on the W here to match the BRL form. Just note that Stephen Boyd explicitly marks this as 0 in his LMI book, and that'll go reduce to a 2x2 matrix, which you can do. I elected to keep the standard BRL form. So I have this here on these off diagonals, so it's a 3x3 block. There's a little bit of criteria to ensure that this works quite correctly, though. So just you got to make sure that this is performed correctly in the setup, being a little bit hand wavy, which I don't like. But essentially, allow this to be 0, and you're not going to run into many issues there. We're feeding through with the U onto the performance output, and then BU, U here, BWW there for the state dynamics update. So similarly, the error is going to be the difference between Z and the Z reference. However, in this problem form, we're not tracking anything, so the Z reference is just going to be 0. We're acting more as just a regulator, rejecting the disturbance from the road. And that's that deviation just from a planar surface. So the feedback law here is going to be U is equal to KZ. So here, I basically am rearranging the state space a little bit. So we have a closed loop system with A and C, and then separately on the outside have the disturbance being modeled with the BW and the DPW. So feeding through on the performance output and then how the state dynamics update. So this is really the newer part. So H2, we had the squared norm here. And it wasn't H infinity norm either. It was the H2 norm that we were working with. But now we're working with the H infinity norm, which is the worst case disturbance here with the W. And we're minimizing that gain of the transfer function W2ZP. ZP is our performance output. And that is explicitly using the L2 gain, so the Lebesgue space or Lebesgue integral. I'm not diving into that too much detail, but you could look at it online. Essentially, it's baking everything through the supremum, so similar to the maximum, but it's not equivalent, where the supremum could be, in the mathematical sense, in the set or not in the set. But in this sense, where it's the least upper bound of the signal gain from ZP over ZW here, right? And that's less than this gamma term. And so when we do the synthesis part, we're actually going to introduce epigraph gamma here. That's just a scalar with the H infinity norm metric. Um, if you remember from the cart pull example for H2, I did a lift, or standard lift is a Z, a new PSD variable, essentially. This is just a scalar, which is nice. But it's a similar concept, right? So like in that instance, we were minimizing the trace of that Z. In this instance, we're minimizing gamma, which would be the least upper bound from this transfer function H infinity norm. Which again has, I'll show later, but it's also the maximum singular value. Cool. So, and this part, I'm skipping a little bit here, but you can look online references too, or the last video. It's pretty similar in the sense of setting up the LMI form and then packaging it into a Schur complement to get it into a nice LMI form. There is one other little wrinkle, which is the linear fractional transform. So on Wikipedia and other sources, you'll see a kind of a general P matrix, or just a P block rather, and that's just the generalized state space that takes in an exogenous input and produces an output. And then you have the controller K on the outside, so then you have a feedback loop with that K. And so that linear fractional transform basically will take that PK and then you package it into minimizing that transfer function there. And then you can break it out into that single line, basically a Lyapunov-like stability criterion with the B and the C performance objectives on the side. And then with the Schur complement, we could package that back into an LMI form. Right now, again, no, where it's not directly convex because we have that bilinear term in P and K. Again, that was similar in the H2 part where we needed to introduce a congruence transform to break it out. And then that, like I said before, that preserves the geometry of the space. A little bit different than the similarity transform, which I'm also going to be using in this part as well for non-dimensionalizing and scaling. So this part looks similar. This is that inverse Lyapunov here, where we can basically do the change of variables, get Q is equal to P inverse. And so Q has a positive definite constraint. And then Y is K times Q. And so that after the congruence transform here, the state feedback of the H infinity LMI is this negative definite constraint here. And then essentially what we're doing here is we're minimizing subject to these decision variables that's concatenated, which is the Q, Y, and gamma. Gamma is this nice scalar here, and it's bounded above with this BRL form here, satisfying this least upper bound, right? So again, I kind of jumped, but this was mapping here to here. And then we have gamma on this diagonal here. And then that's put into the BRL form and it's negative definite. And to back out the controller gain is a similar YQ inverse. Okay. All right. So, okay. So that's some of the boilerplate for the H infinity LMI synthesis problem setup to be convex. And that's how I've modeled it to in my backend. So here, the generalized plant physical performance output. So this part is where I'm mapping the problem to what's stated. Essentially, we have the road disturbance, and we're trying to reject that for a comfortable ride with the pickup truck model. And so we say we're asked that we want to basically minimize, we have this performance criteria that we're trying to optimize towards, which is the ride comfort that immediately is reduced in the body acceleration. So it's not, jumbly like that. We're having a nice smooth ride. The suspension travel, so we want to stay within mechanical limitations, right? We don't want to have crazy tolerances that are absurd with the body and the wheel. So we want to minimize that. And then that was essentially a similar object, or it wasn't objective at that time. It's just a observability on the sea that I modeled. And then the road holding, this one, as aforementioned, is going to be a little bit trickier for the control because the displacement of the wheel is a little bit harder and the road disturbance is unknown. So, but we want to have that in the performance criteria because road holding is important, especially for turning. We don't, we got Ackerman steering. It's not like skid steer where we're trying to violate a holonomic constraint, or we are in the non-holonomic, but that, we want to basically ensure that the road holding tire deflection is modeled correctly here with the XW minus R, minimizing that, and then the actuator effort. And that's similar to that R matrix in optimal control for just penalizing large actuation. And just note, like right here for the U, it's not like there's an explicit constraint like in MPC or something like that. I think I'm going to do that later for constrained control. But essentially, you could model like U actuation input to, or like with this reference governor or a control barrier function or something like that. Something on the input or output that basically kind of governs or makes sure that the U isn't going crazy. But you could also do the clipping too, which I was showing in the cart pull example as well. So now we have this static weighting. So later I'll do more dynamic weighting as a function of the frequency, which kind of looks more like the CISO or PID kind of tuning, a little bit like loop shape. Right now, this is just static, which makes the problem easier just initially to visualize it. But obviously, it's not like advantageous if we're just penalizing. I don't like. We'll see later on, but just penalizing state variables or this performance criterion across dynamics frequency bands that are not really active, so we're just kind of unnecessarily pushing down when there's we'll see in like the Bodhi plots later, like where we might want to shape things a little bit better for the gain and the phase. But for an initial preview, this is, I think, a good spot to just look at a static weighting WQ here, and that's actually CP here. So I kind of mixed it a little bit, but this was Q. This is the weighting. The weighting vector is operating on this Q vector here, which is taking those signals. And so so as I was mentioning, a lot of the literature, you'll just see a general P, which is vague in my opinion, but it's good for, I guess, some of the math that I skipped over. But if you break it apart, essentially we have the plant again, similar to how the H2 is modeled. We have the disturbance. This is just weighted. For right now, I think I just have it as like I or 1. We just have the road disturbance, so just 1. And then that goes into the plant, right? So then it's additive on the outset, and then plucking out signals from the plant here that are completely valid, and the perturb coordinate system with the road disturbance coming in, right? So this is our Q vector, and that's how these weights are being pulled out and then multiplied. So then we have these new outputs, ZA, ZS, ZT from the ZP space. And then we have ZU here for the control effort. And so that's when we're minimizing or trying to optimize towards comfort, suspension, travel, road holding, and effort from these performance criteria. And this is where you could see kind of this, the plant produces the Z. We have the references 0. So then the error is just going to be the perturbance on Z, and that's our controller K on the outside. Cool. I was kind of mentioning this a little bit. This kind of acts a little bit like a Pareto optimal criterion because we have multiple objectives. And so if we eliminate a couple of these, you're going to get a different performance, like objective answer and a different controller. So you kind of have this Pareto frontier, the frontier efficient model, something it's called like that. So you get these different points on this, optimization space that, based off of the weighting performance criteria here, we'll get a different answer. Which is kind of nice and useful, and especially once we get to the dynamic space, we're going to have an augmented plant, but we can then shape it all across frequency bands, which will be useful, especially as a comparison with the mixed sensitivity. Okay, we're almost to the code. All right, so I think that's after this block, yeah. So this is just pushing in the CQ, DQ, performance weight objective. So this is the static weighting right now. So um, right now it's kind of tailored down by a tenth each go around. So we basically have 3 minus 3, 1e minus 4, 1e minus 4, 1e minus 5 weighting. So basically comfort is highest weighted, and then it goes down from there. So the control actuation has the least amount of penalty towards it, and then the suspension travel and road holding are equivalent. So you can kind of tune and play with it if you want, and you'll get different answers, obviously. And then our C, Q, D, Q, and I have A and B above. So now stepping into this is the part where I don't know if I regret or not, but for the cart pull example, I didn't do the non-dimensionalization and scaling. I just used the raw plant. And I think for the carpal, it's probably fine. We're not using crazy units like if I go all the way above, like with the truck, like our scales are much, much different where we have mass of the wheel, mass of the body, the springs are a lot larger. We have the damper at a very large. It's not. We don't have a spring mass damper system on the cart pull, but it could have been a nicety with the units. I don't know, but I digress. I showed a little bit more of the tuning of the tolerances and stuff like that, which I guess is fine. It just kind of gives you perhaps a little bit of a different answer. The one thing that to which will show up. If you don't do this in the H infinity control, you could get into a scenario where I'm going to show the H infinity norm metric actually being violated if you lessen the tolerance too much. And it's going to be proportional by that factor that you lessen the tolerance towards. So that is one thing to be careful of. But anyways, so let's step into this part. So I guess the one caveat here too is if there was constraints on the U, that there should be scaling appropriate on that outset as well, because the U is implicit in this scenario. That's fine for us at this moment, but just something to also be careful of. And yeah, and the reasoning here is to improve the solver numerics too in the landscape. So everything is done with the similarity transform, so the eigenspace is invariant, which again is important for semi-definite programming because we're working with Jordan algebras, and that obviously is directly related to the eigenvalues. So, all right, or yeah, the spectral analysis side of things. So I'm introducing this barred variable here for the scaled synthesis coordinates. So we had the absolute coordinates, we moved to perturbed coordinates, now we have scaled perturbed coordinates. And so here we have SC is that mapping from Z bar to Z. We have SN, the mapping from the barred exogenous input and the control input to R and U, road disturbance, and the control actuator authority. And then SP inverse, so that's the pullback on Q to ZP. So Q was the vector here that we have the weighted performance operating on to get ZP. And so ZP inverse is pulling back on the Q, mapping it to ZP bar and the synthesis side of things. So and then likewise, I introduce a tau, so normalized time scaling, which will scale the dynamic rates. So we have the scaling of the, these signals here, and then we have the scaling of the dynamics itself on the unit or the rates side of things. Sorry. And so that also takes into account the plant dynamic state update here. So we have dz bar d tau now. And so we have to back out with the t ref here, and it's proportional by this t reference, which is defined to be 1e minus 4 down here. And this is all, again, to get it all into order 1, and I'll show that at the end of this code block. So yeah, so basically, once the solver completes, we get a synthesized K bar. And so we're in this non-dimensionalized space. So to get out, basically to back out into the physical force, we do the basically pull back on the Z was SZ inverse. SZ is up here, right? So we get the Z bar, K bar is operating on that. And then we have the U. So we have SU that we have to then apply the K bar to get the U. Kind of complicated, but it's just similarity transforms to get coordinates mapping from non-dimensionalized space back to the dimensionalized coordinates, and scaled appropriately or unscaled appropriately. I'm scaling and non-dimensionalizing, and we're inverting or pulling it back to the original space, which is the perturbance coordinates. Okay, so these are the state scale values. These are the input scale values. These are the performance scale values. So, and then I just basically set up matrices here for SE, SE inverse, SN, SP inverse. That was that T reference, again described here, normalized time scale, scaling the dynamic rates. So that's on the A and the B, and that's scaled. Again, similar up there with that similarity transform. The C and the D here scaled. And so the PZ above here. So the performance weighting value right there, that's what's getting applied to the CZ invert, or sorry, H infinity and DZ H infinity, those two variables there. Did I show that? Yeah. That's that WQ, right? So, okay, cool. And then, oh, guess WQ, you're right. Sorry. So that was the raw, and then we're scaling that appropriately. So then that's WQ. That's what's being operated on in the optimization, let's say, coordinate space. And so the state scales, input scales, this is just printing off a bunch of the stuff up here for the scaling. So here we are. So we can see here we're on a nice kind of order 1 here. Anything to note? Performances are printed off here. I think that's about it. Main thing here is just making sure that we got basically our matrices nice and to order 1 scaling for the problem. So now we put it in, right? So we have the H infinity state feedback control from the quarter car wheel pip module that I compiled for this example. And then, so this is taking in the A scaled, B scaled, the CZ H infinity, DZ H infinity. That's the P. Here, so the CP, DWP. I read it backwards. I read it how the signal actually gets applied to the operator, but same thing. That's what these two are. And we showed it up above here with the PZ and then WQ normalized. Okay, so bottom up. Wait, did I misspeak? See, that's raw. So I think this is just I think this is just diagnostic, actually. Apologies. I think that's just diagnostic. This PZ, I'm using that directly, and I'm using the scale because that's already, yeah. All right. It was a little bit of a misnomer there. Apologies. That might have been hanging around. Okay, cool. So here is the optimum of the H infinity, state feedback, synthesis. And so we have our K scaled, okay? And then if we unscale it, obviously it's we got much larger control gains at the moment. But in the scaled coordinates, it's you know, about 3 units larger. Um, But we saw a fast and efficient 10, optimal, no issues. Didn't have to touch the solver config either, which is nice. And that's like, so again, the solver configs like tolerance level is like 1e minus 5, 6. And then the regularization is very minimal. So like 1e minus 12 or 14 even. So it means the curvature of the problem is actually pretty well posed. When I did this non-dimensionalization and backed out and got a scaled K. And then I'm showing the closed loop poles here, which I think I'll plot later. So yeah, that's this part so far. And so now for the weighted performance realization and H infinity norm. So this is the part here to just ensure. Sorry, I just want to make. I think I do plot. Huh. Maybe I'm plotting later. Sorry, I'm probably plotting later. Whatever. It's minus minus, so left hand plane. Um, so the weighted performance realization H infinity norm. So yeah, the certificate here is essentially this part on the actual transfer function of the closed loop system. Again, we have the barred space now, which is that non-dimensionalized perturbed coordinate system. And so that we have the CCL. This takes essentially the same exact transfer function that you would do in like a linear systems class, but just note that the transfer function is looking at the W to ZP channel, right? So that's the H infinity norm. And we want to make sure that it's bounded by the gamma K that we synthesized above. And again, that's going to be in this uh, non-dimensionalized space. Um, am I missing anything? I think everything's pretty straightforward. So the one thing, yeah, again, we have this d tau, right? So the dz bar d tau from the T reference. Scaled feedback law there. That's our transfer function as a function of j omega or s frequency. So really here is the part where we're evaluating this H infinity norm, which is equivalent to the maximum singular value, right? So that max singular value of the responses of that transfer function here. So we have the CCL, and then this is j omega I minus ACL. And then this is just, instead of doing a pseudo inverse here, this is just a least squares back solve on BCL here on the right hand side. And so we do that multiplied by the CCL, and then we have plus DCL on the other side here, right? So we have this response here. We take the singular value decomposition, where it's like the U sigma V, and then we essentially are getting the largest gain. So singular values are ordered, greatest to low at least, right? Yeah, in descending order. And so the gain here is if it's greater than the peak gain, we just reset the gain and the frequency of which the peak is at. And so, and this is just setting up the initial values here. This is just, again, basically an arrangement from the log space for scaled frequencies that we're getting the maximum singular value of the transfer function there. So we get the B scaled W, B scaled U, and then W onto the performance, U onto the performance, feed through. That's estimating the norm here. So we got the scaled frequency omega, I think it's radians per second, and then the scaled norm there. And what we're trying to assert is that this is absolutely less than the synthesized gamma K, acting as that H infinity certificate that we're minimizing in the problem. And so this is just, is it bounded, right? Is the passive bounded? Um, so we can see that the passive system is not bounded, right? And then the active system is bounded. And then they both have the peaks at this radians per tau. So it's a normalized coordinate system, so it looks a little weird. I forgot it's not radians per second, it's radians per this tau unit that we've introduced above, a little funky. So our tolerance, we were really riding up on the margin of that norm and the gamma, which is pretty nice. And it's actually, like I said, it's on the tolerance or the order of which I thought the solver tolerance is at, which is 1e minus 5, which is great. I mean, that's exactly what we were looking for. And that's our gamma k again in this normalized coordinates. So just to summarize, because this was a little bit more dense, I guess, less plots. I'm going to plot more, I think, late at this next part, but yeah, just do a really, really brief recap here. So we found the static weight H infinity feedback. We have this LMI form here founded from the bounded real lemma. And I did a little bit of a skip here with the linear fractional transform. You can look at that on Wikipedia or something like that. It will use that generalized P and K as aforementioned. I broke the P, that generalized state space, into individual blocks and signals to make it a little bit more diagnostic and easier to read to which I'm posing this problem. And I'm plucking those signals out of the plant, and then I have the weighting matrix here, right? And then those are the performance criterion defined as this Q vector, right? And so we have this ride comfort, suspension travel, road holding, and actuator effort, all basically factors that we're trying to minimize towards in our objective function. And similar to the H2, where we had an epigraph Z variable, which was positive semi-definite, this is just a scalar gamma, which is nice. And so we have this kind of epigraph. Well, it is an epigraph gamma, but it's really from this least upper bound of the supremum of the worst case disturbance gain on the closed loop transfer function from W to ZP. And so we had the LMI synthesis, the problem posed above, setting up the problem. This was newer for non-dimensionalized and scaling the problem to make it better for the primal dual interior point method that I have on the back end, which solves the semi-definite program, and it's really nicely posed. Just making sure that the coordinate systems are applied correctly with the similarity transform. That's different than the congruence transform, which we broke out the bilinear term to actually set up a convex problem. And then this was setting up this was dimensionalizing, scaling. This was solving the problem. And then this was the realization here and actually asserting that the H infinity norm criterion was successful. And then as showed, it is in contrast to the passive system, which is not. And it's small, but it's in this this non-dimensionalized space. So we can see that passive is not robust with the H infinity norm metric with that disturbance here, W to ZP, whereas the active control is. And that's exactly the goal here. We're trying to reject disturbances per the criterion that we've defined above. And so, yeah, I think that's all. So this next one, I'm going to walk through the observer side. So again, the dual problem of H infinity, it'll be an H infinity observer. And then I'm going to connect the state feedback with the observer in the same way as H2 to get a dynamic compensator. And then we're going to analyze that compensator. And yeah, I think that'll be part 4. So thanks for joining. I hope you all have a good rest of your day. Thanks.